Let's begin this module by briefly acknowledging some of the individuals whose work has helped to shape the view of theoretic models, theories, and paradigms that structures this chapter, this textbook, and this course. Starting alphabetically and with the people most responsible for the development of the semantic view of theories, we have Nancy Cartwright, currently the Distinguished Chair Professor at the Tsinghua University in Taiwan. The late Ronald Geary, who was my thesis advisor and spent most of his later career at the Center for Philosophy of Science at the University of Minnesota. Frederick Suppy, who's at the Texas Tech Center in Seville, Spain. The late Patrick Suppes, who spent most of his career at Stanford University. And Bas van Fraassen, who's currently a distinguished professor at San Francisco State and an emeritus professor at Princeton. The person who is most responsible for the paradigmatic notion of scientific progression is probably Thomas Kuhn, who spent most of his later career prior to his death at Massachusetts Institute of Technology. Finally, the person most responsible for my distinction between dynamical and attributional theories is Robert Cummins, who's a emeritus professor at the University of California, Davis. On the view that structures this text and course, theories are collections of models. That is, they're just structures. These structures contain elements that represent categories that correspond to features of the world. These representations have interrelationships within these structures, these models, that mirror the relations between the things that the categories pick out in the domain. When theorists predict, retrodict, manipulate, and explain, they manipulate the elements of the structure in order to generate a solution to a particular problem, to make a prediction or a retrodiction, or to figure out how best to manipulate a system to determine an outcome. So how might one get their heads around the idea that theories are collections of individual theoretic models, and that theoretic models are simply structures, the elements of which correspond to features in the domain, then the relationships between those elements in the structure correspond to real relationships between those features in the world? Well, when it came to theoretic models, Geary's favorite metaphor for illustrating this idea was to point to a map. Geary would pull up a map like this map here of Long Beach, and he would say, look, here is a structure. This structure has a bunch of spatial dimensions and a bunch of individual features. So, for instance, there's a representation of the Long Beach Museum of Art and the Queen Mary and Long Beach Airport, Trader Joe's, Cal State Long Beach. There's representations of waterways and highways and surface roads. And all of these features are related to each other in a way that mirrors their relationship in the city of Long Beach. So this structure has elements. Those elements correspond to individual features of the city of Long Beach, and the relationships between those elements correspond to the spatial relationships between those elements in the city of Long Beach. For that reason, we're able to use maps to figure out how to get from one place to another, to estimate how far it is, and so on. Now, I never had a chance to talk to Geary about that metaphor after Google Maps became so sophisticated and ubiquitous, but I'm sure he must have loved it, because now Google Maps isn't just a single theoretic model, it's a collection of models. So in a way, it's a theory about what's in Long Beach and how to get around in it. For instance, suppose that you want to see what Long Beach looks like in a non-schematic way. You can change your model by introducing a complexity to the model, by superimposing on that relationship of individual places, roads, waterways, and so on, the satellite map of Long Beach. If you want, say, for instance, to zoom in closer, you can then create a model that's just preserving the features around Cal State Long Beach. Say you want to go grocery shopping later. Well, then you can modify that original model so that it explicitly represents grocery stores and their spatial relationships to each other and to Cal State Long Beach. Suppose you say, hey, I want to go to Ralph's. You can select routes, hit directions. And now Google Maps introduces a new modification of that original structure that illustrates the relationships that you want to take advantage of to get from Cal State Long Beach to Ralph's. So Google is like a theory of how to get around in a city like Long Beach, or really any place that you have a map of. It's a collection of individual theoretic models. They all are modifications of a basic structure that captures the spatial relationships and important features of the city of Long Beach. Thus, under the semantic view of theories, we can see theoretical models working in much the same way as other models, for instance, architectural models or anatomical models. Each of these models represents features of the world and relationships between those features, and they represent those features and relationships only in certain respects and only to certain degrees. Consider, for instance, the semantic view notion that there is no canonical means of representing or presenting or formulating a theory. For instance, when we think about the ideal pendulum law, we might think of its typical algebraic formulation that dates back to the time of Christian Huygens. But we could also represent that relationship using a state space diagram that shows the relationship between arm length and periodicity. We could represent it geometrically in the way that Galileo did when he originally discovered the relationship, or we could represent it in terms of a phase portrait, as is done here for the dynamic systems characterization of pendulum motion. Theoretic models, however, do differ from other models in that they have two very specific representational, predictive, and manipulative goals. Dynamical theoretical models try to create a model of the dynamical evolution of a particular phenomenon or system through time as a function of the interrelationship of the component elements. So a dynamical model will break down a more complex phenomenon into a set of component elements and their relationships and model the evolution of that set of phenomenon through time in terms of the relationships between those component elements. For example, the ideal pendulum law is a dynamical theoretical model. It relates periodicity to the length of the pendulum arm and the force of gravitational attraction. And so it then allows us to understand how the pendulum bob will move through the arc swing over time. Similarly, the ideal gas law represents the relationship between the pressure and volume of a gas and its temperature. This illustrates a nice point about dynamical models. They don't necessarily have to have a temporal category included in their formulation. The ideal pendulum law has P, periodicity, which is a temporal category, but the ideal gas law has no explicit representation of time. The T in the ideal gas law simply refers to temperature. It's a dynamical model, nevertheless, because that relationship expressed in the equation between pressure, volume, and temperature is one that can be manipulated by changing one or the other over time. The other class of theoretic models are attributional models. Theoretic models that attribute specific properties to objects, events, or relations, or that offer theoretic models for why or how objects, events, or relations have specific properties, are attributional models. Uniform gravitational acceleration is an example of an attributional model. It tells us that all matter has the property of accelerating uniformly within the Earth's gravitational field at the rate of 9.81 meters per second squared. At least we're in fact completely accurate in all places on the planet. Another example is the attributional model of the molecular structure of water. Water is H2O. Water in nature, of course, contains all sorts of dissolved minerals and so on. And perhaps even more important, hydrogen and oxygen have several isotopes that can also form water, perhaps the most famous being heavy water or deuterium-2O. Oxygen isotopes include O17 and O18. Hydrogen isotopes include H2, D2, and and H3 or tritium oxide. Tritium-2O is both radioactive and corrosive, though strictly speaking, it still is water.